because biomass has many utilizations. So all of it, we need to utilize all of the biomass if we want to be efficient. Otherwise, we are utilizing only a very small part for the biofuel, and that is not very efficient, and that has consequences. But okay, I will not go into the details for now for that. And we look at sustainable development indicators. So, for example, we can look at SDGs and other kinds of indicators. Yeah. And transportation is a very big part also that uses fuel. So transportation is also something that we study with the assessment of convention vehicles, electric vehicles, and so on, which is now very popular. And I will talk a little bit about electric vehicles today as well to show you what is the thing from that. Yeah. And another thing is buildings. Buildings is also a very big user of energy. So that is why buildings is also part of the scope that we study. So we look at energy efficiency, renewable energy in buildings, net zero energy buildings, energy positive buildings, and so on. So these are the kind of studies that we focus on. And let's move forward. Yeah. Okay, it's moving. Yeah, it started to move now. So today we'll talk about energy and environment. So normally, traditionally speaking, when we talk about the basic necessities of our life, we have food, clothing, and shelter. But actually, even energy is a very basic necessity of life. We cannot survive without energy, right? We absolutely need energy. And when in the early days, before even agriculture, we were hunter-gatherers. We picked up fruit from the trees or something like this and just took whatever was available in nature for our food. At that time, fire was our source of energy, our only source of energy. Yeah, fire. I think somebody has your microphone on. May I request people to have the microphones off so that we don't have disturbance in between? No, thank you so much. And then we became the agricultural society or pre-industrial agricultural society. Then our source of energy was like buffalo. Yeah, so when we were hunter-gatherers, our source of energy was only human power, right, and fire. But now, along with human power, which is limited, we also have buffalo or some other animals that provide us energy. For example, the horses or camels, and so on. And then we also use the primitive form of wind energy. So we had the windmills for irrigation and so on. So this was our sources of energy. But maybe about 200 to 300 years ago, we discovered fossil fuels. And then started the industrialization. So we had the Industrial Revolution. First, we discovered coal, then oil, gas, and so on. And we became more and more efficient to use those energy forms. And our life became much more comfortable because of that, because of the energy that we were using from the fossil fuels. But probably all of you already know that fossil fuels are basically produced from biomass over many millions of years. So when trees or marine life, etc., they died and they were buried under the earth, and they, under the very high temperature and pressure of the earth, they got converted, the biomass on the land got converted to coal, and the biomass in the marine life got converted to oil and gas and so on. So that was these fuels are very energy dense. That means they're very efficient to use for energy. However, we know now that there are several problems associated with the use of fossil fuels. First of all, the use of energy fuels, the energy resources are non-renewable. So that means we have a limited amount of those resources, and they are being produced, but they take millions of years to produce. But when we use them very fast. We just dig them out of the ground and we are burning them to get energy. So now we are using non-renewable resources very fast. So there is an issue that we are going to face shortages. That is one. The other thing is all these fuels like coal, oil, or natural gas, they are carbon based. Yeah. So because they are carbon based, when we burn them to get energy, we produce carbon dioxide, which is a greenhouse gas. I think all of you know that very well. And along with that, they also produce other gases such as sulfur dioxide, NOx, and so on, which are not good for the environment. So we have all these issues, all the environmental impacts that are associated with energy, and we must consider that. And today we are going to talk about life cycle assessment and how this kind of tool helps to assess energy systems. So before I go into the life cycle assessment of it, I want to talk about the concept, the idea. Now, there is the Earth itself. I think somebody is raising the hand. I don't know because they want to ask some question right now or no. Okay. So maybe we'll have question answers at the end of the of my talk. So then there will be a session where we can discuss this. Okay. So maybe it is better that way. We have the Earth itself has a carrying capacity. Okay. The Earth can take care of the waste. You see, before human beings started to produce a lot of waste, the Earth was taking care of all the waste by themselves. However, the Earth has a certain limit of the amount of waste that it can take care of. If we exceed those limits, sorry, there is a lot of disturbance everywhere, so I'm getting a bit distracted with that. I'm not used to it. So, okay. So, the Earth has a certain capacity of waste that it can carry, but with the population increase, yeah, and the amount of chemicals that we are producing, such as pesticides and fertilizers, etc., which the Earth is not familiar with, that is creating a lot of problem, and the Earth is not able to handle those waste. Okay, and then we have several problems associated with that. But as I said, the Earth has a certain carrying capacity, and we want to find out what that limit, what that carrying capacity is. So a group of scientists in the year 2009, actually, they first defined 9 planetary boundaries. Okay, so there are 9 planetary boundaries that you can see over here. This study is a later version of the 2009 study from 2015. And so they have these planetary boundaries for climate change, biodiversity, land use, freshwater use, biochemical systems, etc. And the point is that how are we doing with respect to these planetary boundaries? So you can see that if you look at climate change, then things don't move according to the way they should. So if you look at climate change, we are in the yellow zone. The yellow zone is high risk or increasing risk zone. So already in 2015, we are in the increasing risk zone. And the red zone, the biodiversity is in the red zone. So we are already beyond the risk of, beyond uncertainty, we are in the very high risk zone. If you look at biochemical flows, such as phosphorus and nitrogen, we are already in the red zone. Land use is in the yellow zone. So you see, we are not doing very well with so many different things of these planetary boundaries already in 2015. We are already in 2022, and we have not improved, okay? So, but the point I'm trying to say over here is, one is that we are coming very close to the planetary boundaries or even exceeding them. And the other thing is that these impacts, these categories are interrelated. So climate change is related to land use. Land use is related to biodiversity. When we grow agricultural crops, we affect freshwater use, and we also affect the biochemical flows because we introduce fertilizers, nitrogen and phosphorus, which is already we are in the red zone. And then there is, I do not know what is flashing on my screen. It's very difficult. So all these things are interrelated. So the thing is, now we are talking nowadays a lot about climate change. We are talking about net zero, carbon neutrality or something like this. But if we focus only on climate change, only on greenhouse gas emissions, then we have an issue. Because supposing we say we want to focus on climate change and we want to reduce greenhouse gas emissions, and we say, okay, let us now try to reduce greenhouse gas emissions by moving from fossil fuels to biofuels. But when we increase biofuels, we need more land. So we affect land system. Then we put more fertilizers. So we affect biochemical flows. We put more water, freshwater use. So we affect freshwater use. So you see, all these things are actually interconnected. They are not isolated. So if we just say, I will focus only on trying to reduce greenhouse gas emissions, but I don't care about the other things, then I have a problem. Because in trying to reduce greenhouse gas emissions, I may increase the stress on freshwater use. I may increase the stress on land use. I may increase the stress on biochemical flows. So all of these things are working together, and we should not look at only one impact in isolation, because the whole system of the earth is interlinked and we have to look at those together. So why do we need, this is what we mean by a life cycle perspective, and why do we need a life cycle perspective? So let us illustrate that by looking at an electric car. Nowadays, electric cars are being promoted for their help for the environment. We say that an electric car is less polluting than conventional cars. Now, if we take a city like Jakarta, and if we introduce electric cars in the city, that would be a very good thing, because it would reduce the local pollution in the city. So we don't need to do any assessment. We can directly see from by our observation only that when we drive diesel car or gasoline car, we emit a lot of fumes. But if we use electric cars, which is powered by a battery, by electricity, then we will not have these kind of what we call tailpipe emissions. So from the perspective of urban air pollution, the electric car would be very good. But we have to look at it from a life cycle perspective. So we look at the entire life cycle. Here, then we see that, okay, electric cars don't produce tailpipe emissions, but they run on electricity. So there is no emission occurring at the car itself, but the electricity that we use to drive the car also needs to be produced. And that is typically produced at some power plant, maybe a coal-fired power plant, maybe a natural gas-fired power plant, and so on. So what we have done essentially is we have transferred the pollution from the car to the power plant. The efficiency of a power plant, for example, the efficiency of a coal-fired power plant may be about 35 to 40%, which means that to produce 1 unit of electricity, I need to put in 3 or even 4 units of coal into the power plant, because there will also be losses from transmission and so on. So to get that 1 unit of electricity at the car as the final energy, I need to produce much more electricity I need to put in much more primary fuels at the power plant. So that means I do have pollution. I have not removed the pollution. I have only shifted it from the car to the power plant. And in fact, I may even increase the pollution if I'm using fossil fuels because of the conversion efficiencies and so on. The point now I'm trying to make over here is not that electric cars are bad, but it would be not correct if we just assess the environmental benefit of electric cars just by looking at the car itself. The fair assessment would be to look at the entire life cycle, which includes the power production, which includes the manufacture of the car, which includes the manufacture of the battery, yeah, And all these things need to be included. And same for the conventional car. We need to include all of these life cycle stages in the comparison. So then we can make a more fair comparison. Okay. So that is the main point about life cycle assessment, that we need to look at all the life cycle stages. And what we saw in the previous slide, that we should not focus only on one impact category, but we should look at multiple impact categories to avoid problem shifting from one impact category to another impact category, which means if we try to reduce greenhouse gas emission, we should not then increase pressure on freshwater use. That is not very smart, right? We need to try to find a solution, an environmental solution that is comprehensive, and it tackles all impact categories, not just one or two. Okay. So that is a very important point of a life cycle assessment, or what we call holistic thinking or systems thinking. So here, many times I like to use this diagram of an elephant. So all of us who are looking at this picture can see that it is an elephant. However, there are 6 people on this slide who are blindfolded. So they are not seeing that it is an elephant. They are only feeling different parts of an elephant and making interpretation based on what they feel. So somebody who feels the ear of the elephant, you see on the top over here, this person thinks that it's a fan. Somebody who's feeling the tusk of the elephant thinks it's a spear. Somebody feels the trunk of the elephant thinks it's a snake. Somebody feels the tail of the elephant thinks it's a rope. There are 6 different people feeling 6 different parts of the elephant and making interpretation for what it is. But none of them knows that it's an elephant. And that is a problem, right? But all of us, we are life cycle people, so we look at the whole elephant so that we can solve the entire problem. That is the main message about life cycle assessment. And I will try to illustrate this to you through many examples, starting with, of course, the electric car and so on. Okay. So life cycle assessment is a tool for environmental assessment where we look at the entire life cycle of any product or service. And when we say entire life cycle, we mean, you can see over here, we start from the extraction of raw materials from which the product is made, then manufacture the product, package it and distribute it, use it, and end of life. So we look at all life cycle stages to avoid shifting of the problem from one life cycle stage to another life cycle stage. And we also look at multiple impact categories, not only carbon footprint or greenhouse gas emissions, but also water footprint, ecosystem quality, natural resources, human health, etc. Because we want to avoid shifting the problem from one impact category to another impact category. Okay, so 2 things. First, we look at all life cycle stages because we want to avoid problem shifting from one life cycle stage to another life cycle stage. And we want to look at all impact categories, not just one of them, because we want to avoid problem shifting from one impact category to another impact category. So this is the very important advantage of life cycle assessment. Okay. So here again, this is just an example of a PET bottle, but illustrating the same thing. This is a water bottle. It is made from PET, which is a kind of plastic. And so we have to first extract the raw materials. So plastic, as you know, is made from oil. So we need to extract the oil from the ground. So when we extract the oil from the ground, we need resources, we need energy. And that is related to emissions to air, emissions to water, use of resources, which will have impacts on human health, ecosystems, and resource use. Yeah, so these are our areas of protection. So we need to consider all this. Then the oil which we have pumped out of the ground needs to be transported. The transportation can be done via the pipeline or via the oil tankers, the ships, big ships, etc. And that will also use fuels, etc. When we'll have emissions to air and water, and these will have also impacts. So that also needs to be considered. Then where we have the refinery in which the pellets, the plastic pellets will be produced. And then we have the bottle through injection molding or blow molding. We produce a bottle, we pack it, we fill water inside and pack it. Then we send it to the convenience store where it will stay inside the refrigerator. All these activities will also have use of resources, use of energy, and impacts associated with which we must consider. And then finally, we will drink the water and we will throw the bottle away. It may either be reused or it will be recycled, or it can go to the landfill, or it can go for incineration. And all these things will also have impacts. Okay, so all these impacts need to be considered. So even for a simple product like a bottle, we have so many things to consider. Okay. So what is life cycle assessment, or LCA? LCA is an environmental assessment tool for the evaluation impacts that a product or service has on the environment over the entire period of its life. So the main, this is a very long definition. So I have highlighted the main points, which is, okay, first of all, LCA is a tool for environmental assessment, and it considers the entire life of the product. So when we say entire life, we mean extraction of the raw materials from which it is made, manufacturing, packaging, marketing, use, reuse, and maintenance at the end of its useful life. Yeah, so all these things we need to consider in the life cycle assessment. So ISO 14000 series is dealing with environmental management systems. So ISO 14001 deals with environmental management systems, and ISO 14040 and ISO 14044, they deal with life cycle assessment. Okay, these are the two basic standards for life cycle assessment. Of course, there are other standards for carbon footprint, water footprint, and so on. We will not go into that for now. Okay. Now, according to the ISO 14040, the life cycle framework is that we start with the goal and scope definition. So in the goal, we define the objective of the study, and then the scope is the system boundary. Then we collect data, which is the inventory analysis, data about inputs. So what kind of resources we use, what kind of energy we use, or how much we use, and what were the emissions to air, water, soil, etc. This we collect in the inventory analysis. And then we have the impact assessment, where we convert the inventory items into potential environmental impacts such as global warming or acidification, eutrophication, freshwater use, and so on. Or we could go to the end point and have impacts on human health, impacts on ecosystem quality, or impact on resources. And then finally, we did all those studies, and then we have interpretation, where we look at environmental hotspots. So we look at which parts of the life cycle contribute a lot to the environmental impacts, so that we can focus on what we need to do to reduce those environmental impacts, and which impacts are giving high, big damage. So we look at that and try to reduce that. And then there are many applications of life cycle assessment. So traditionally, the most traditional use of life cycle assessments, product development and improvement. So life cycle assessment as a tool was developed by production engineers when they were looking for eco design. And so, but later on, environmental scientists, they developed the theories behind how to make the measurements. Okay. And then it's also used in strategic planning by companies, etc. It is used in public policy making, marketing, and so on. So the various stages of life cycle assessment are goal and scope definition. So first we define the objective of a study. Of course, we must know what it is that we want to assess and why we want to assess it, right? Before we start the study. That is very important. So that is the goal of the study. And then we have to define system boundary, because, there are so many things we can include. So you could, include the whole universe in a life cycle assessment, but we don't want to do that. We don't have the time for that, and it's not meaningful to do so. So we have defined what is important we will include in the study, and what is less important maybe we want to leave out, so that in the interest of time, in the interest of budget, and so on. And we have to define a functional unit, which is the what we call the quantification of the function of a product. Okay, so all calculations will be done based on that. Okay, I will not go into the detail of that for now because okay, it's a very short time we have. And then we collect data about the inventory. So we collect data on the inputs, which is resource use and energy, and outputs, which are pollutants and wastes that are coming out. Okay, and then we convert the inventory items into potential impacts, and finally we interpret. Yeah, where we define the key life cycle stages, the most significant life cycle inventory or impact assessment items, and then we make recommendations on how to improve. So when we do the life cycle assessment, we start here with the data collection. So we look at the data for the raw materials, we look at the data for the emissions and so on, and then we convert them into potential environmental impacts, either at the midpoint stage, we call it here, like climate change, resource depletion, land use, water use, and so on, or we look at it in the final damage stage, which is the human health, ecosystem quality, and resource depletion. So this is some little bit of just general background about life cycle assessment. Normally, I'm teaching a 3-credit course on life cycle assessment, which is for 45 hours. So of course, today I have only 1.5, 2 hours. So I will give a very, very brief idea about what we do. Just share some examples with you so that you can see how a life cycle assessment is utilized. And then if you're interested to use it for your work, then of course, then you can do more. You can study more about it. You can contact me also. There are books available. There are many things can be done. And when we look at the impacts, as I told you that we have impacts at the midpoint stage and at the endpoint stage. So at the midpoint stage, we look at impacts such as climate change in terms of kilograms of carbon dioxide equivalent, or by looking at the radiative forcing that these greenhouse gases such as carbon dioxide, methane, nitrous oxide, CFCs, etc., they are performing. So how much infrared radiation they can capture. And we use carbon dioxide as the reference gas. Yeah. And then convert all other greenhouse gases into carbon dioxide equivalent so that we can aggregate them. We can add them up together and get a single value. Similarly, we do that for ozone depletion, acidification, eutrophication, etc., according to their own units and the things. So that is at the midpoint level. And at the endpoint level, we look at the 3 final damages, which is here at the disability adjusted life years. So we look at the human health impacts of climate change or ozone depletion and so on. And then we look at the ecosystem quality damage in terms of potentially disappeared fraction or some other units, depending on which method we use for acidification, eutrophication, and so on. And for the resources, or what we call the abiotic resources, which means the resources such as minerals, fossil fuels, etc., we look at the ores and we look at the extra energy required in megajoules for extracting the next bit of ore. So that is what we consider. Okay, so this is some very basic theory. I know it is very complicated if you are not already familiar with life cycle assessment, but I introduced it just for the sake of completeness so that at least you know that this is there. But now we will focus our talk mainly on greenhouse gas emissions, etc., simply because it is very famous and people understand climate change a lot, right? So let us start with a few examples to illustrate how a life cycle assessment is done. So since we talked a little bit about electric vehicles, so if you want to do life cycle assessment for vehicles, there are 2 life cycles to consider over here. In the green dotted line, you have the vehicle life cycle assessment, and in the blue dotted line, you have the energy life cycle. Okay, so there are 2 life cycles. So let us talk about first the vehicle life cycle. So when we manufacture the vehicle, we have, the vehicle is composed of maybe iron, aluminium, glass, many materials, right? So those, first we need to extract those resources from the ground. Then they will be processed into the material, and then the component of the car will be manufactured. So we have to manufacture the body, the chassis of the car, or the window of the car, or the engine of the car. All these things need to be manufactured. then they will be assembled together. And all these things have to use resources, energy, and they will have emissions and impacts on the environment, which is why we are considering them. And then we will use the car, and finally there will be the end of the life of the car. We will either recycle some of the materials, or some of it will be incinerated, or some will be landfill. So this is the vehicle life cycle. And for the energy life cycle, so supposing we are talking about a car that is running on gasoline, then we have to extract the oil from the ground. That is now we are talking about the well to wheel, or the life cycle of the energy carrier. So we have to extract the crude oil from the ground, then we have to transport it and then refine the oil to produce diesel. And then that diesel has to be transported, and then it'll be put inside the vehicle. And then when we operate the car, we will burn the diesel to move the car forward, so that will have emissions and so on. Or if we're having an electric car, then we will have to produce electricity. So the electricity may be produced from coal, natural gas, or whatever. So then we have to extract that resource and produce the energy, and then we have to put it into the battery. The battery will be charged and so on. Okay. So this is basically what we would do when we do the life cycle assessment of a vehicle, and we want to compare the electric car with a diesel car or something like this. Okay, so let us see now what an life cycle assessment would look like. So I want to show you that, so that you can now see. I mean, this was, until now we are discussing a little bit theoretically, so it's kind of vague for you. But when you see the result, maybe it will become more clear what we are doing. So now over here, we have life cycle assessment of battery electric vehicles, or electric vehicles, as compared to conventional vehicle. So what we are doing here, there's a lot of information over here. So let me spend some time with you to explain what is this there on this graph, so that you can understand better what it is. So here on the y-axis, we are plotting some kind of environmental impact. For example, it could be greenhouse gas emissions. So we can present greenhouse gas emissions as kilograms of carbon dioxide equivalent. And in the x-axis, we are plotting the distance that will be traveled by the car. Okay. So normally you would expect that as we travel more distance, then the impacts will increase, which is correct. However, even before we have traveled the first kilometer, we are at 0 kilometers, already we have some impact. And that impact is coming from the manufacture of the car vehicle. So in case of an EV, an electric vehicle, this impact is also more significant, even more significant than a conventional car, because we have the battery production. So not only do we have the manufacture of the car, but we also have the manufacture of the battery, and all that adds up. So already at 0 kilometers, our carbon dioxide or our greenhouse gas emission is over here. Okay. And then as we drive, you look at this black line over here. As we drive the car, we use electricity. So our emissions keep increasing as we drive more and more. Now, when we look at a conventional car, the conventional car also has to be produced. Maybe it does not have a battery, that at least that very big battery. So then our emissions for the production of the car are lower. They're here. You see the electric car was over here, but the battery car is over here, which is lower. But when we drive the car, for the conventional car, when we drive it, the emissions are higher because we are using maybe some fossil fuel, which has higher emissions. So you see the slope of this red line is higher than the slope of the black line. And so at some point, which we call the break-even point, then they cross over. So before that, at some distance, which we call D, for example, say maybe I don't know how many kilometers, 1,000 kilometers or whatever. So before we reach that break-even point, the electric car actually is having higher emissions than the conventional car. You see? But once we reach this break-even point, then the conventional car, the red line, becomes higher than the black line, which means the conventional car is having more emissions than the battery electric vehicle. So, of course, what will be the slope of the battery electric vehicle depends on how is the electricity produced. So if we have green electricity production, which is this green dotted line over here, which means that we are producing electricity from largely from renewables and not so much from fossil fuels, then the slope will be low. So you can see the green line, green dotted line has a lower slope than the black line. Yeah, because the emissions are lower because we are using green or renewable energy. So the production emissions are high, but the break-even point, the intersection with the red line comes faster than with the black line. Yeah. So more quickly, the battery electric vehicle in the green case becomes better than the conventional vehicle. Yeah. On the other hand, if we are producing electricity from coal, which is very bad, then we have the blue line over here, the blue dotted line on the top. And you see the slope of that is very high. It is almost, it seems to be higher than even the conventional vehicle, or at least parallel to the conventional vehicle. So in that case, you see that the electric vehicle is always worse than the conventional vehicle. We will never break even until the end of life. So you see, if somebody asks you, is electric car better for the environment or not? What will be your answer? It depends. It depends on how we produce the battery, how we dispose the battery, how we produce the electricity. All these factors need to be considered. That means we need to consider the entire life cycle. Yeah. We cannot make a decision just by, it's not a blank check. We cannot just say, yeah, electric car is better or electric car is worse. We cannot say like that. We need to make this kind of study, do a comparisons, and under certain conditions that need to be maintained, then the electric car will be actually better than the conventional vehicle. So these kind of studies are very important. So even policymakers, when they do these kind of studies, they have to make sure that they are looking at these aspects, not just make, oh, biofuel is good for environment, finish. No, not like that. And I will show you examples of that even, of what happens if we make decisions like that, and why we need to look at life cycle assessment for assessing energy and environment. Okay. Okay, so this was some kind of a theoretical example with the electric vehicle, but let me show you some real results that we have done or study in Thailand on electric buses. So here you see we are comparing three kinds of buses. EB is the electric bus, CNGB is the compressed natural gas bus, that is the bus running on compressed natural gas, and DB is the diesel bus running on diesel. And then we are having the three environmental damages, that is damage to human health, damage to ecosystem, and resource depletion. So here, when you look at the EB, and you look, there are the bar is divided into two parts. One is the yellow part and one is the blue part. The yellow part is the production phase, including recycling at the end of life, etc. And the blue part is the use phase, when we are driving the car. So when you look at the production phase only, the yellow part, you see that the electric bus has higher impact than compressed natural gas bus, as well as than diesel bus. And that is true for human health, that is true for ecosystem damage, and it is also true for resource depletion. But we are life cycle people, we don't consider only production, we consider the entire life, including the use phase. So when we add the use phase, then you see that the electric bus actually becomes better than the compressed natural gas bus and the diesel bus. So we have happy ending. Yeah. In this case, the electric bus is working for all three impact categories. The electric bus is working out to be better than the compressed natural gas bus and the diesel bus. Of course, this study has been made with many assumptions and many contexts. The context is very important. For example, how the electricity was produced. So we used the electricity mix of Thailand, okay, which has about a certain 8% or something of renewable energy. But what if we didn't have renewable energy inside the electricity mix? How would that affect the result? And that is something that we need to also see. So we did a sensitivity analysis to see that if we change the electricity mix, how will the results of the study change? So here now we have done this sensitivity analysis. So there are many items on this graph, but let me simplify for you. So EB, this EB here, the third bar, is the normal bus as using the electricity as it is now in Thailand. But we can increase the renewable mix of the, as we are planning, everybody's talking about carbon neutrality, etc. And they want to increase the renewable energy part in the electricity mix. So if we increase the the renewable energy in the electricity mix to 25%, you see, of course, as we expect, the EB, the electric bus, gets even better because now the emissions from electricity are even lower. And if we increase to 40%, as according to the government plan, then we will get even better. But what if there was no renewable energy inside the electricity mix? That is EB 0%. Of course, we get a bit worse. You see, the EB 0% is worse than the EB. But if we compare it still, even the EB 0%, we compare with the compressed natural gas bus and the diesel bus, it is still better. So here we are kind of more confident of our results that even if the electricity mix was not as good as it is today, and if it was worse, even then we could say that the electric bus would perform better than the compressed natural gas bus or the diesel bus. In fact, we also looked at, okay, for the compressed natural gas bus, it was heavier. So we used a different material, kind of a polymer material or a fiber to reduce the weight of the bus so that the fuel efficiency would increase. So that is this bar over here, you see. But even then, this bar over here, this is the conventional one and this is the improved one. But even the improved compressed natural gas bus is still worse than the electric bus. So the electric bus is actually better for all impacts: human health, damage to ecosystem, as well as resource depletion. So this is what the life cycle assessment told us. Okay, so this is one example, and I want to now show you many other examples to see how life cycle assessment is useful for us. So we will look at the life cycle greenhouse gas emissions, or what we call the carbon footprint, from various ways of energy conversion. Okay. So as I told you, we should not look only at carbon footprint actually, but okay, this is just for illustration. But later on, I will show you an example of biofuels where we will look at other impacts as well. But just for the sake of illustration, I'm using just one impact category to show you the effect of using life cycle. So we will consider power production from many sources. So we start with, as a baseline, we will use fossil fuel, the natural power production from natural gas. And then we have many renewables like mini hydropower, biomass, solar PV, wind, and so on. And we will compare it with the fossil fuels to see whether the renewable energies are actually having lower life cycle greenhouse gas emissions or not. Because, we are always promoting renewables because we said we want to reduce greenhouse gas emissions. Yeah. So let's see whether the renewables are actually better in terms of greenhouse gas emissions than the fossil fuel or not. So when we consider the life cycle assessment of natural gas power production, then we have the entire life cycle like this. So if we extract the natural gas, here in this case, we extract it from the Gulf of Thailand, and then that is transported via pipelines to the natural gas separation plant, where we separate other gases from the natural gas. And then that natural gas is purified and sent into the power production system where we burn it to produce electricity. And of course, there will be exhaust gases and wastewater and solid waste, etc. All these things need to be considered when we are considering the life cycle greenhouse gas emissions. Okay. So greenhouse gas emissions from all these steps are considered. So what does it look like? So now we had, when we did this study was done many years ago, but we had two kinds of power plants. We had thermal power plants and combined cycle power plants. So if you look at the bright blue bar, that is from the burning of the natural gas. Yeah. The bright blue bar is from the burning of the natural gas, which is only the use phase. But there is also an upstream, which is over here in the extraction of the natural gas and the production, etc. So that is this part, which is much smaller than the use when you burn the natural gas, but it is still not zero. It is quite substantial. It's about 10% or so. So it is quite large. And this is the thermal power plant, and this is the combined cycle power plant. The combined cycle is more efficient than the thermal power plant, and plus it does not use oil. This one uses some oil sometimes. Okay, so what I want you to remember for the next 5 or 7 minutes is this value. Okay, so let's take a value of 600 kilograms of carbon dioxide equivalent per megawatt hour, and we will use this as the benchmark to compare with the with electricity production from renewable sources and see how the renewable sources are compared to the fossil fuel, in this case, natural gas. So remember this value for the next few minutes, 600, okay? 600 kilograms of carbon dioxide equivalent per megawatt hour. Now, we studied the mini hydropower plants in Thailand. So mini hydropower plants are actually supposed to be quite good for the environment because, first of all, they don't have a big dam. So you know that when we build big dam, reservoir, etc., for power production, that has big impacts, environmental impacts, because we have to flood certain portions of land which has methane emissions. And we also have social impacts because we have to move a lot of people and they are displaced and they will have problems. Yeah. But for mini hydropower plants, we don't have a big dam there because in the mountainous regions, the water is flowing very fast. So it will turn the turbine and we can produce electricity. But anyway, we still have some construction to do, all this weir, power intake, head race, etc. And that will have certain environmental impacts. And then we have the operation and maintenance, and finally demolition, etc. All these things will be there. So we cannot say that the electricity from mini hydropower power plant has zero emission. Okay, it is not correct. We cannot say that it is, even the carbon dioxide emission or greenhouse gas emission is zero. We cannot say that. No, it is not zero. But how much is it? So here, when we look at the different stages, we find that for one particular power plant, it was 13.3, or let's say 13 kilograms of carbon dioxide equivalent per megawatt hour. Or we took the average of Thailand, it was about 18 kilograms of carbon dioxide equivalent per megawatt hour. Okay, so it is not zero. But now I remind you, in the previous, for the natural gas power plant, we said 600 kilograms of carbon dioxide equivalent per megawatt hour. So as compared to 618 is extremely low. Yeah. So that means that the mini hydropower plant is doing much, much better than the natural gas power plant, even though it is not zero. Okay. Similarly, if you look at the PV photovoltaics, yeah. So here we did the life cycle assessment for the photovoltaics in Thailand. Okay, there are many processes, especially the production of the cell. The solar cell is a very energy intensive material. It uses energy intensive material. So it has very high emissions at that stage, yeah, because it uses a lot of electricity and so on. Nevertheless, when we looked at BIPV, or the building integrated photovoltaic, so instead of the roof, we replaced part of the roof with photovoltaic cells. And then depending on where the cells are manufactured, whether in Germany or Japan or Thailand, China or Thailand, we have this kind of numbers over here. So let us look at Thailand, for example. So this bar over here is after we account for some part of the roof is replaced by PV. And this bar over here is if we did not replace the roof, but just put the solar PV. But even if you consider this one where we don't replace the roof, you see the emission is about 80 grams of carbon dioxide equivalent per kilowatt hour, which is the same as 80 kilograms carbon dioxide equivalent per megawatt hour. So remember, compared to 600, it is much lower. It is not zero. Sometimes policymakers get very angry when we say, oh, solar PV is not zero emission, because they want to believe it is zero emission. But from a life cycle perspective, it is not zero emission. However, having said that, we can clearly see that it is much lower. And in fact, if we have a building integrated PV, then it becomes only 20 kilograms of CO2 equivalent per megawatt hour, which is much, much lower than 600, right? And if our electricity was clean like in Germany or Japan, it would get even lower. Yeah, something like that. So that is PV. Then if you look at wind, once again, the wind turbine has to be manufactured. So we have to extract materials to manufacture the wind turbine. Many of the materials that we use inside the wind turbine are rare materials. So they have high impact because they're not abundant in nature. Yeah. So all these things also, so again, once again, when we consider the life cycle, then our emissions are about 40 to 160 kilograms of CO2 equivalent per megawatt hour. So once again, not zero, but lower than 600, right? So it is lower than natural gas. And in fact, if we consider coal is even higher than natural gas. The emissions from coal would be about 1,000 kilograms of carbon dioxide equivalent per megawatt hour. Yeah. So then the wind turbines would be even better. Yeah. And if you look at biomass, so here we did the life cycle biomass, we looked at rice straw. So at the time when we did the study, rice straw was considered as a waste. So we did not consider the upstream, which is a paddy cultivation. We did not include in the life cycle, but we started from the collection of the straw and the baling of the straw and transporting the straw, etc. And then we found out that the emissions are 28 kilograms of carbon dioxide equivalent per megawatt hour. Once again, not zero, but much, much lower than 600 kilograms CO2 equivalent per megawatt hour, which was the emissions for natural gas power production. Yeah. So once again, biomass also work out to be better. So here you see the power of life cycle assessment for making these kind of decisions. So now that was the story with greenhouse gas emissions. I will now try to expand beyond greenhouse gas emissions to look at other impacts from biomass. So I will take the case of biofuels. Okay. Now we consider biofuels to be green. You know, biofuels, we are talking about either bioethanol or biodiesel. Yeah. So in Thailand, bioethanol is produced from sugarcane molasses, from cassava, and a little bit from sugarcane juice. Whereas biodiesel is produced from palm oil. And even in Indonesia, I think it is quite similar. These are the feedstock that are used for ethanol production and for biodiesel production, right? Now, why do we consider biofuels as green? Green as in environmentally friendly. Why? The reason for that is that biofuels are produced from biomass, and when that biomass is growing, it takes up carbon dioxide from the atmosphere for photosynthesis. So the carbon inside the biomass is coming from the inorganic carbon in the atmosphere, right? It takes up the carbon dioxide from the atmosphere and builds its starch and sugars, etc., inside the body. And when we convert that biomass to biofuel and we burn the biofuel in the car, that carbon gets released as carbon dioxide. So what we are saying, oh, but that carbon dioxide that we took, that we released when we are using the biofuel is equal to the carbon dioxide that we absorbed when we were growing the biomass. So it is carbon neutral. So people talk about carbon neutral, but that is old story. Okay, we are life cycle people. We have to always remember the elephant. So we cannot say that that is the full story. This is only one part of the story. When we are growing the biomass, it is not only photosynthesis that happens. Photosynthesis happens, of course, but along with that, we have to provide water to the crops. We have to provide fertilizer to the crops. That also uses energy and resources. So for water, we need to pump the water. So that requires energy. For fertilizers, they need to be manufactured, which requires energy. Especially nitrogen fertilizers are very energy intensive. So, and usually the energy that we use for manufacturing the fertilizers is non-renewable, fossil energy. So that will also have greenhouse gas and other emissions. And then when we apply nitrogen fertilizers to for cultivation, there are emissions of nitrous oxide, which is a very strong greenhouse gas. It is almost 300 times as strong as carbon dioxide. So that also needs to be considered. Yeah. And then there is a whole chain in between. So we have to cultivate the biomass, we have to harvest the biomass, we have to transport it, we have to convert it to biofuel. And all these things also require energy, they require resources, and thus they also have emissions to the environment. Yeah. So that means that we have other emissions. I did not say CO2, I put CO2e simply to specify that we are talking about greenhouse gases, not only carbon dioxide. Okay. There can be other greenhouse gases such as methane, nitrous oxide, etc., which are also important. So that is why I said CO2e. So that means that there are net greenhouse gas emissions from the biofuel life cycle. It is not free from, it is not carbon neutral. Okay. But as we saw for the case of rice straw just in the previous slide, the emissions can be low. But when we look at the life cycle, we may see a different story, and I will show you that. Because now we said we start the biomass life cycle from the cultivation of the biomass. But actually there is also a step before cultivation, which can be land use change. And this is a very, very important thing, land use change. Why? Because sometimes if we are converting forests to agriculture for the sake of planting feedstock for biomass, that can be pretty disastrous, because forest land, especially tropical forests or peatlands, etc., they are very, very big stock and very big sink of carbon. In the soil of a tropical forest, which is mature tropical forest, which may be many 100 years old, there is a lot of carbon stored in the soil. So when we cut down the tree of the forest and we prepare the land to plant the feedstock for the biofuel, then we release a lot of the carbon that is stored in the soil. We release a lot of the carbon. And that can be so huge that any benefit that we can get from the life cycle of the biofuel is already lost here in the first stage when we convert the land. So this is something that we have to be very careful about. If we have land use change, then it is extremely difficult, I would say impossible, to maintain the greenhouse gas reduction benefits of biofuels. So once again, the point is not that biofuels are bad, but if we intend to promote biofuels for the sake of reducing greenhouse gas emissions, then we have to be careful about which kind of land is converted to agriculture, because that will have a significant bearing on the overall life cycle greenhouse gas emissions. And I will show you some examples. So here, these are the examples from Thailand. We have done many studies about ethanol. So let me run you through this slide. What is shown over here is greenhouse gas emissions from cassava ethanol and molasses ethanol. And the numbers are represented over here in grams of carbon dioxide equivalent per megajoule of ethanol. So first, let us focus on this red line, red dotted line here. So this red dotted line here represents gasoline, which we are going to replace with ethanol, right? So the gasoline has an emission, a life cycle greenhouse gas emission of 90 grams carbon dioxide equivalent per megajoule. So that means if you want to say that ethanol is better than gasoline and we should use it to replace gasoline, then the value should surely be lower than 90, right? Otherwise, there's no point to replace it, right? We will not gain. Let us see what happens. When we don't consider land use change, supposing that we are planting on a land which has been in agriculture for many, many years already, we did not convert some forest or something. So there, our values, depending on the many conditions of agriculture, etc., how we are planting it, how we are the cassava, how we are planting it, what kind of water, fertilizer, etc. we use, the values of the greenhouse gas emissions are varying between 27 to 91, or let's say 30 to 90 grams of carbon dioxide equivalent per megajoule. So in the upper limit, if we are not doing very well, supposing we are using coal in the distillation of ethanol, because ethanol requires high amount of energy for distillation and dehydration, because we need to remove the water to make the ethanol into fuel grade. If we use coal over there, then we may have like 91 grams of CO2 equivalent per megajoule, which is worse than gasoline. So there is no advantage at all. But if we can use biomass in the distillation process, etc., maybe we are in the lower end of about 30 grams of CO2 equivalent per megajoule. So then we are doing better. So that is an important information for us. So it is not that just because we produce ethanol from cassava, automatically it becomes better than gasoline. Not necessary. It depends on what we are using as the fuel source. Similarly, if we convert grassland to crops, so if we convert a grassland to cassava, then you see we are between 60 to 130. So the benefits are not so much. We might not even get a benefit. But if we convert forest land to cassava, finish. You see the emissions are more than 250 grams of carbon dioxide equivalent per megajoule, which is much, much higher than 90. So there is absolutely no advantage. So we cannot convert forest land into cassava, and for the reason to promote ethanol for reducing greenhouse gas emissions. It doesn't work. Okay, let us look at molasses. Molasses is also the similar story. We have a range over here if we don't have land use change. For grassland also, we are doing worse. And if we convert forests, we are like 300, we are doing worse. 300 or so grams of carbon dioxide equivalent per megajoule, which is much, much higher than 90. So that would not be very good. So these things we have to keep in mind when we are making policies or making decisions about whether we want to replace gasoline with ethanol for reducing the greenhouse gas emissions. Similarly, similar stories for palm biodiesel, but much better. So here, our baseline for comparison is diesel, not gasoline, because normally we replace diesel with biodiesel. So then the diesel is about 85 grams of carbon dioxide equivalent per megajoule. But here, if we don't have land use change, our emissions are about 18 to 38, which means like, let's say 20 to 40 grams, which is much lower than 85. So we are doing very good. Palm is very good because palm is a tree. It can stock a lot of carbon, which is why the advantage comes. Even if we convert rubber to oil palm, we are even lower. Cassava, if we convert to oil palm, we are very low. Paddy field, if we convert to oil palm, we are very low. So for all these cases, palm oil is actually quite good in terms of greenhouse gas emissions. What will happen to the other emissions? That is a secret, which I will tell you a little bit later. But if we convert forest land to oil palm, sorry, we are here at 220 to 250 grams of CO2 equivalent per megajoule, then we are not going to have advantage from greenhouse gas emission reduction. So conversion of forest to oil palm, or not even, this is forest, but if you convert peatland, it will be even worse. So that is not acceptable. We will not get greenhouse gas emissions benefits. Okay. So once again, life cycle assessment is giving us this kind of result. Now, I want to show you what happens when we consider other impacts in addition to greenhouse gas emissions. Okay. Policymakers focus usually a lot on greenhouse gas emissions and energy because that is their priority, right? They want to increase energy security. They want to reduce fossil fuel use. They want to reduce imports of fossil fuels, and they want to reduce carbon dioxide. Yeah. So they focus on these two. Now, what I'm showing over here is I'm comparing 4 different fuels. The purple line over here is for diesel, which is our reference fuel. And these 3 are, the first 3 are biodiesels. The first one is FAME, which is fatty acid methyl ester, which is another name for biodiesel. Okay. And then we have the red line, which is the H-FAME, which is hydrogenated FAME. Okay. We have one extra process of hydrogenation in the biodiesel. and we get a better quality fuel. It's a better quality fuel than FAME. Okay? We can blend more. Like, for example, the auto manufacturers, they don't allow us to manufacture more than, don't allow us to blend more than 20% of biodiesel in diesel, because they say that we cannot guarantee about the engine if you mix more. But for HFAME, you can mix more because it's a higher quality fuel. And same for BHD, or biohydrogenated diesel, which is also an advanced biofuel that can be produced from, among other things, from palm oil. Yeah, and that is also an advanced fuel. Okay, and that also you can blend more. So FAME has some limit of blending above which we cannot blend. Actually, in Indonesia, I think we are blending more than 20% already, like 30% or something, right? Yeah. So, but normally car manufacturers are not allowing us to put so much. Okay. So when we consider the two favorite categories that policymakers like to consider, that is global warming and fossil resources, we see that diesel is bad, and the other three, biofuels, you see these three lines are much, much lower than diesel, both for that, for the fossil resource scarcity as well as for global warming. So if the policy makers are to make a decision based on only these two things, fossil resources and greenhouse gas emissions, no problem, biofuels are good, we should go for biofuels. But biofuels, you know, are having agriculture. Fossil fuels don't have agriculture. So if we look at other impact categories, which are more related with agriculture, that is in the green box now, the acidification, eutrophication, toxicity, etc., land use, there you are seeing that the picture is reversed. Now the biofuels are not doing very well as compared to diesel. So this is a very important message. So in other words, what we have done is we have shifted the problem from greenhouse gas emissions to acidification or eutrophication or land use. So the problem is not gone. We have only shifted it to something else. And this is something that we have to be aware about. Okay. And once again, my point is not that biofuels are bad, but it is not, my point is that it is not enough to look only at fossil resources and global warming and make decision based on that. We should also look at other impact categories, because we want to have overall improvement, not just improve one thing, but spoil another thing, right? So that is why it is very important that we look at all categories and then try to improve our process in such a way that we are also reducing other impacts. Yeah, because if we didn't look at the other impacts, then we don't know anything about that and we did not care, and things can get much worse. Yeah, but if we look at the other impacts, which is the whole point of doing life cycle assessment, then we will see this point and it becomes very clear to us that we need to do something. So in kind of a summary, what are the key takeaways that we get from this? First is we cannot do without energy. Okay. We need energy. It is necessary for survival, but we need to have life cycle thinking to avoid problem shifting between life cycle stages, to avoid problem shifting between impact categories. And we did not talk about sustainability so much. We focused only on life cycle assessment, which is environmental assessment, but there is also economic and social assessments for sustainability. And so we should do the whole sustainability. So life cycle thinking also prevents shifting of problem from between sustainability pillars. So shifting between, we try to improve environment, but we spoil economy. That is not acceptable. Or we try to improve economy, but we have social problems. That is also not acceptable, right? So there also we need to look at the entire elephant. Yeah, we have to look at the entire elephant in the room. We also saw that renewable energy is not emission free, but of course, in most cases, it is much better than fossil energy from fossil fuels. Yeah, but for biofuels, of course, we saw that there are pluses and minuses. That is something that we need to take care of. Yeah. Another thing that I did not talk much about, but I would like to kind of say is energy efficiency is desirable, but it's not the final solution. Here, what I would like to point here is that sometimes we think that, okay, we just improve the efficiency, then finished, we have done our job. However, this is actually not the case. And the reason for saying this is energy efficiency usually is also associated with rebound effects. So what happens is that when the energy efficiency increases, then people start to use even more. And the advantage that we gain from energy efficiency is lost by the increased use. So many years ago, when coal was first discovered, like in the 1800s, we used coal rather inefficiently because we didn't have the good machines or the steam engine, etc. But after the steam engine was developed, the utilization of coal became more efficient. So of course, we were expecting that now the use of coal will reduce because we are using it more efficiently. But what happened was that the use of coal increased. How did that happen? Because of efficiency, it became cheaper to use coal. So more and more applications of coal were developed, and we started to use more coal. So we increased the efficiency, but we ultimately use more coal. I'll give you another example for the car. Right now, the fuel prices are very high. Yeah. So people are using less car because the fuel hurts the pocket. If I were to make the car so efficient that the fuel cost matter less, because I can drive long distances with a single liter of gasoline, the effect of that we would think that, okay, so now I will use less gasoline, right? Because the car has become more efficient. But the consequence of that is going to be people will use the car more and more because now fuel is cheap. So they will live more far away from the university and drive long distances because they want to have big bungalow. You cannot have in the middle of Jakarta or in the middle of Semarang, you cannot afford to have big bungalow unless you are a very rich man. But if you go to the outskirts of the city where land is cheap, you can afford to have a very big house, right? And it is no problem, I'll just drive to work. And then even when you have any leisure time, you will drive more because car is efficient, fuel is cheap. So ultimately, the overall effect is going to be that you will use more fuel instead of less fuel. So once again, it does not mean that we should not have energy efficiency. Of course, we need to have energy efficiency, but along with that, we have to be careful also that we need to have sustainable consumption, which is very important, without which we will not be able to avoid rebound effects and we will end up using more than before, even with a higher efficiency. Okay, so with that, I would like to end my talk for now, but I would like to open for any discussion or questions, etc. Thank you for your listening. I'm very glad that I was here and have this opportunity to talk with all of you. So slide.
Thank you very much, Prof. Sabir, for a very interesting subject to deliver. And now we come to the question and answer sessions. We have three questions in the chat box that maybe you can respond, Prof. Sabir. First is from Suhaib Hassan Sens from Superior University. He has questions. What do you think that ISO 50,001 to be considered as beneficial for energy and ISO 14,001 for environment?
Yes, that is absolutely correct. ISO 15,000 and 50,001 is for energy purposes, and 14,001 is for environmental purposes. Of course, they are quite related also in a way, because as you saw that energy is responsible for a lot of the environmental impacts, right? So in that sense, when we improve the energy situation, we will of course improve the environment situation as well. But as you saw also that when we talk about environment, there are many things to consider, not just the amount of energy that we use, but also other chemicals or other materials that we use. So the environmental assessment is broader than just the energy part, right? Energy part is one part of the environment.
Okay, thank you very much, Prof. Sabir. The second question is coming from Ira Fitriana. She's our PhD student at Doctoral Program of Environmental Sciences. She has three questions. The first one is regarding steps in conducting LCA. Could you give more explanation to step 3? How we transform life cycle inventory into impact?
Okay, yeah. So yeah, I did not go into the details of that because the time was rather short, and normally we go into a lot of discussion. So what we do is, so when we collect the data for the inventory, so we collect data like how many kilograms of iron we used, how many kilograms of coal we used, how many kilograms of carbon dioxide we emitted, something like that, right? So in the early days of life cycle assessment, we use that only as for as the, what can I say, the proxy for environmental impact. But as you know that these are inventory items, these are not the direct impacts. But when we use some resource, or when we have emission of carbon dioxide or sulfur dioxide into the environment, what is going to be its impact? So for example, carbon dioxide or methane, they have impact on global warming. How much is that impact? So then there are methodologies that we have devised for converting the inventory item into the impact. Similarly, for the sulfur dioxide, how much is the impact on acidification? We have some methods that are developed. Different people have developed different methods. There are more than one method for that. So we have developed methods to convert just the emission of something into impact. And that step is the life cycle impact assessment step. So there are many methods available for that. Like, for example, there is one popular method called recipe. There is another method called impact. There are some other methods like the CML method or EDIP, eco-scarcity. There are many methods, or in USA they use Tracy. So these kind of impact assessment methods are there that normally we have software that can convert these inventory items. We put them in the software, it helps us to convert them into potential impacts. And we can also, I mean, you don't even need software. Sometimes you can just use the characterization factors that are available, and you can use even an Excel sheet to do the calculations. Okay, that is a different point. But basically what we do is that we convert emissions or resource use into potential environmental impacts by using certain methods, impact assessment methods that have been developed, and some characterization factors have been developed for that. Does that somehow answer your question? Yeah.
Yeah, thank you very much, Prof. Sabir. For the second questions from Ira, Also, step in number 4, how we can identify the key life cycle stage of the system. How we can identify the key
Yes, okay. Sorry about that. Some internet problem, so I got muted and then out of the system. So I hope that now you can hear me. So the question that we are addressing is how to find out which is the key life cycle stage. So when we do the life cycle assessment, that time we can see that. So for example, if you remember the slide, I will put it up again just for you to see. So here you can see in this slide that when we look at the electric bus, for example, so here we see that this yellow part is for the production phase, which has recycling in it, and the blue one more having more impacts than the production phase. So this is kind of one example when we want to see which life cycle phase is the key contributor or something like that. I hope that kind of somewhat answers your question. And there was a third question.
Maybe it's already, or maybe you can ask.
Buzzing.
Okay, yeah, you remember. Okay, maybe for the participants who raise hand, can start the questions, please. Bu Baslina.
Hello, can can you see, can you hear my voice? Sorry, sir.
Yes.
Okay.
Okay. Hello, Achan Sabir. Actually, I am your student in KMUTT, already graduate in 2014 from Indonesia.
Oh, okay.
Okay. I would like to ask, actually, I already study in your class, but I want to ask more about the LCA. Has the LCA study become one of the components that must be carried out by the industry to run the project that estimate the competitiveness of the product that they produce?
Well, I'm not sure about Indonesia, but in Thailand, there is no requirement to do an LCA, but there is no regulation, but there is a market force. For example, carbon footprint is one of the components inside an LCA, and that for many industries that has become a market force because consumers, you know, the clients of the companies, they demand that you must give us the carbon footprint value, or you go for labels. So in that case, then it becomes a requirement. In Indonesia, I do not know exactly, but there is something called proper. Yeah, maybe somebody from BRIN or somebody can explain if they are there on the. There is a regulation in Indonesia already called proper, where the industries have to do life cycle assessment. So I think for Indonesia, it has become even more a requirement.
Yeah, but not like in Thailand. Right? And may I ask the second question?
Yet, but we have been doing like this.
Sorry,
yes,
the network is not good. Can I say the second question?
I can hear you.
Okay. How about the life cycle cost of the product? How can this affect the calculate of the LCA framework, the LCA study? If we say the life cycle costing of the product.
Well, life cycle costing is an economic tool, and I cannot talk about it today, but it's quite an interesting topic as well. So what we do in life cycle costing is that we include the entire life cycle and the cost of the product, just like we did for environment, we did the environmental impact. For life cycle costing, we do the cost, and it is used in combination with life cycle assessment. Now, in life costing, there can be two types. In one is you just do the costing as economic calculation and finish. The other type is where it's called full cost accounting, in which you monetize or you monitorize the environmental and social impacts and include that also in the life cycle cost. So in that case, then the environmental impacts are also coming into the life cycle costing as monetized values, as you internalize the externalities. So that could be another way.
Yeah, I see. Yeah, because that I do in a community, and some of the teacher, Achan said me to sit in your class to do also the LCA framework, not only the LCC. Okay. Thank you, Achan.
I have lost you.
Yeah. Oh, sorry, you cannot
Yeah,
hear.
I lost you for some time, a few
Oh,
seconds.
okay. Yeah, because you said that the LCA and LCA and LCC, the relationship of them. So in my study in community, I do the LCC, and some Achan said I have to sit in your class to do LCA also. Thank you, Achan.
Okay. Yes, can you, somebody else had also raised the hand, but now it is gone. I'm not sure. Somebody raised the hand apart from Baslina. But I did not notice who it was. Was it Mo Agus? Oh, Amar Sharaf Eldin said, ask about the data of LCA, also the name of LCA software and how we can process the data. Well, data collection is a very important and cumbersome part of lifecycle assessment. So that's a very big story. But there are also many databases available for background data such as EcoInvent and others. Yeah. Or we even have national databases in Thailand. We have, and I think in Indonesia also you are developing a national database. I think BRIN, you should ask BRIN for more information. They are the right people to ask. And about software, there are many software that are available. So some software are free software, like some software are free software like OpenLCA, and many that we use are paid software like SEMA Pro or Gabi or stuff like that. No. Okay, there was one question before and one question after. Let me. My research is on LCA, but I find it difficult to collect data, especially regarding LCI in Indonesia. Very limited LCI data from government and SEMA Pro software. What strategies can I do? Work hard. That's how you have to start. We all started that way. I started lifecycle assessment more than 20 years ago. There was no data existing. So you have to try and as much as you can find the data, use other studies to get proxy data, then try to adapt data to Indonesian situation. So for example, if you have some databases, then they are not relevant directly to you. You can change some things inside that. For example, you can get some of the information about how much electricity is used, but you can use the electricity mix of Indonesia and things like that. So that is how normally you would have to do it. But there is no easy solution around data. What we can do is that, and sometimes when you don't have enough data, we make certain reasonable assumptions based on other studies, and then we do sensitivity analysis to show what range of values our study results will vary depending on how far the data is from the data that we have assumed. I hope that somehow answers a little bit your question, because if you want more details than that, you have to come and join my course. How to overcome the constraints of different systems, different statistical information, the use of different products in one product by different researchers at the same time in LCA. Well, this is life. Life is complicated. So we will have different systems and we will have different statistical information. In fact, since you mentioned statistical information, doing uncertainty analysis along with sensitivity analysis helps you to get data, because a lot of times we tend to present data as a single number or results as a single number, but things vary. So normally we may do scenarios analysis, we may do sensitivity analysis, and we may do uncertainty analysis, and then present the results in that way. So there will be, like I showed you in one of my slides for the what you call that, if I can find my slide. Yeah, but I don't know, but others cannot see them. Others cannot see my slide. Yeah. Let me share the screen. Yeah, so now for example, here you see the values are present the range. So that is the result of looking at many scenarios together from different systems. Yeah. Let me stop the sharing. Maybe it's creating problem. Present the results like this, because you see when you want to answer the question, what is the greenhouse gas emissions from cassava ethanol? There is not one answer, because there are different things. So something somehow to answer your numbers rather than one single number, to show that okay, it can vary answers your
Okay.
Okay, so I'm very sorry we have some problem with the internet. So let us now continue with the question and answers. Sorry about that. I keep losing the connection.
Yeah, anybody want to?
Anybody would like to have any questions? I think that now we are back. Sorry.
Okay, let's still have question. Yeah.
Yes, somebody has made a comment in the chat that uncertainty and sensitivity analysis should be carried out in proper way in LCA study, as we could not rely on the quality of data and also factors. Absolutely. I can only say that I agree with you 100%. Yes, that's true. Because we have problem with the quality of data always, and also the characterization factors, etc. So yes, to have meaningful results, it is very important that we do uncertainty and sensitivity analysis in life cycle assessment. Actually, in any scientific study, actually, but yes, in life cycle studies as well. Because yeah, life is uncertain. So that is just the reality of life. We can't avoid it, but what we can do is we can characterize it, we can assess it, and put a number to it so that we can make reasonable statements, meaningful statements. Yes. So thank you, Ms. Prapti.
Okay. And any other questions from the audience? We are sorry to have internet connection in our faculty, and now since the internet is back.
Well, proper. Somebody asked me what proper I meant. Proper is the name of some regulation in India, in Indonesia. Yeah.
We have one question, Miss, before Prapti. Yeah, the question is from Dian. Our homework in Indonesia is if the actual or valid data from our country, either primary or secondary data, and then put them into database system. Those many people could use the database to do the LCA in Indonesia context. So this is not questions, but remark. So if you have, if you want to respond this question, this remark is also okay.
Yes, of course. I can only remark that I hope BRIN and other related agencies are listening, because that is always a big problem, that even if we have databases, sometimes the agencies have their hands tied because of confidentiality agreements, etc. with industry, and they find it difficult to share that information. But I absolutely 100% agree with you.
Yeah, I'm not sure if a question from Mulyadi is already answered. How to overcome the constraints of different systems, different statistical information. Okay, you already answered that question. Okay. Thank you, Prof. Sabir. Any other question? Maybe one or two. You can ask directly via direct questions using raise hand.
We have one from Prapti Mandari.
Okay, from Prapti again.
Okay, thank you very much. I'm so sorry I turned off the camera because I wonder whether the connection is stable or not if I turn on the camera. So sorry. Uh, I will give a response to Pak Mulyadi, Prof. Maybe he asked
Thank
about
you.
the proper mean about my statement in doing uncertainty and sensitivity analysis, not the proper program under Indonesia government. So proper mean in this way is it is carried out in many method in carried out sensitive analysis. For example, we can use the what we call it the distribution, which is a different method with the following Gauss distribution or log standard mean distribution, etc. And I think EPD International already mentioned in their rule whenever we carry out NLS LCA study for getting EPD document, if I'm not mistaken. They mentioned clearly that the sensitivity analysis should be carried out under log mean distribution, log standard mean distribution on Monte Carlo simulation. That is my response on Pak Mulyadi. Thank you very much.
Okay, thank you very much, Prapti, for responding question from Pak Mulyadi.
Thank
Any
you,
other
Prof.
questions by direct? Yeah, yeah. Thank you. Questions? Okay, I think all the audience is already satisfied to your answer, Prof. Sabir, and the time is already 11:30, and we have to end up this discussion now. And I can conclude that LCA is very important right now, not only for industry but also for academia. And I hope you all the knowledge that extracted from Prof. Sabir, and will use it for your. Okay, we will have another general lecture tomorrow, special and PhD students. It is regarding how to write a scientific for international or national journal, or we can say that how to article. Yeah, Prof. Sabir experience for this writing article. He has I think tomorrow you will have a very good experience, especially for the students, master and PhD students. Thank you very much, Prof. Sabir, for your coming today, and also to all the audience for your actively participations. And see you tomorrow for scientific writing courses at the same time, yeah, at 9:30. Thank you again,
Thank you.
and see you tomorrow. Wassalamualaikum warahmatullahi wabarakatuh.